Okay, good morning. Can you hear me? Thank you very much for coming this early. I know because now we are in the daylight saving time. It's even earlier. In the last session, we start session and waiting for students for a while. That is why I summarily make an announcement that, okay, now we are in the daylight saving time. So if you think the session is 1 hour later, no, please come now. Well, anyway, thank you very much for coming this early. Anyway, we can take this time to address questions. If you have any questions, you can ask me now while we are waiting for the others to join. Oh, I have a question about assignment 3. And the question was, should we show the question and the answer? Well, that is very much depends on you. The only important thing is in your recording, in your screen recording, please try to, not please try, you need to demonstrate that you have generated the questions that has been allocated to you, the 5 questions, and show that you have chosen 3 out of that. While you're doing that, which questions you are addressing is basically clear. Of course, I would recommend you to go to the question and try to explain the options. Anyway, that makes things easier. If I were you, I would think that way of like reading on a screen and explain the options and why that is right and why the others are not right. That is the most straightforward way to do that. Well, I cannot be more specific of that, but it's easier to review the previous sessions and maybe take some idea from myself. I explain the questions usually in such a way, and usually, but I would sometimes include more explanation. You can simplify my answers. Well, there is another question about assignment 2. Oh, that is a little bit quick. We will try to finish the marking in 2.5 weeks. We have a large number of students doing that. We try to do that as fast as possible, but we have the limit of capacity. Another is the seed of A3 released. Well, yes. Let me share my screen. So if you go to announcement, the seed is here. And also, I have made available all the past questions. Remember, in the past, because the quiz is limited to in-class completion, so after the due time, we hide the questions, and now I have republished everything. Sure. As our people still growing, and we are now something like 5-6 minutes into the session, let's start our discussion. As usual, we will have a review anyway. So yeah, let's do it. Well, as usual, let's have a review of the big picture. We studied machine learning as software 2.0. Okay, we want the machine to program themselves, and to achieve that, we would need experience in the sense of a machine. It refers to data. We need to believe there is some trend to learn from data that can generalize to unobserved situations trend. We do not have explicit description of the trend. If we do, we program the machine rather than let the machine do themselves. Second, we discussed our framework of doing so. Given the data, we first fixed a range of hypotheses from which we would like to learn what is the trend. And to be specific, in this subject, we consider the trend as some relationship between well, observable part of the data and a prediction target. And the candidates in the hypothesis set, each one of them represent a relationship from X to Y. And we want using a selector to select one of the candidates to describe that according to some criteria. And in the next two lectures, we considered a particular setup of the framework in which our hypothesis is to take the data attributes. If you consider data as a table, each column corresponds to something that each data sample needs to describe, defines it, as a property of each sample. We think those attributes we consider a computational model in such a way. We take the weighted sum of those attributes. We give them weights, we take the sum, and we have a number. And then anything that follows is from this number. We use this particular one number to make decisions on the sample. And we have formed geometric understanding of this. We consider maybe one data attribute as one axis. This form, I got a small question here. I will address that later. Okay, this form a data space. Well, in the space, the computed number can be thought as, if you consider one particular number as some color, it would be like a paint the space in some way. In the linear case, we will paint the space along with a gradient along some direction. The direction is given as W. And the computational model can be interpreted as computing the projection of our data points onto the vector W. And in the next two lectures, we considered another possibility of making data models where we adopt if-else like test of individual data samples. And we learned how to design data structures so that instead of using programming explicitly, we can build the data structure and link the data structure together to make an tree-like architecture. Decision making will be corresponding to going through the nodes in the tree and with the leaf nodes corresponding to decisions, and inside there, those intrinsic nodes represent some testing condition on the data attributes, and to decide which subpopulation we are going to investigate more. And to make the decision criteria, we have discussed the criteria of measuring the purity or uncertainty in the target value. We use entropy to measure how certain or how uncertain distribution is. Okay, but that corresponds to the intuitive notion of purity, how pure or how mixed of some random variable. However, this is more intuitive. This has many implementations, not only limited to sorry, let me, I just feel I'm now using another screen today. Okay, well, that corresponds to multiple ways implementation, multiple ways of implementation. And entropy is a particular quantity in information theory that helps us to measure the optimal way of encoding some random variable. Okay. Yeah, in week 7, we reviewed the picture and we have considered the big uncertainty of this learning paradigm, of this learning strategy. We realized that the entire learning is a stochastic process. It's of some random, there is some internal randomness. So where does that come from? We can consider the prediction on some particular H test, well, X test. And if we apply the learned H star to here, we will get a prediction of test. And this is a random variable. It is stochastic. Why this is random? Not because this particular data sample, but because this is a result of a random process. And where the randomness comes from, for all those parts, we can fix, but for this part, the input, the training data, there is intrinsic randomness, and therefore the result is random. And we have analyzed this randomness because the resulted learned hypothesis is random, everything from it is random as well. And the randomness is from the training samples. For all the resulted stochasticities, for all the resulted randomness, we are particularly interested in one thing, that is the realized performance of a model. So if we evaluate a model on a data, how well or how poorly the model has performed depends on the data itself, not only on the true merit, not only on how good H is, but also on how lucky it is to encounter some data. However, here we consider luckiness as we will have an evaluation that is close to the out of sample generalization correctness of the hypothesis some particular age. Okay, if the difference is exceeding some tolerance, we think that is a bad luck. And our guarantee is that the bad luck happens with less and less probability, and the decrease is exponential. Okay. With respect to the number of training samples. This is natural. If you have a lot of samples and you evaluate performance on a lot of samples, it tends to be more reliable. It's unlikely that this measurement differs from the true performance with large amount. Okay. And in week 8, we have considered a particular way of composing advanced machine learning models from sample ones. In particular, we considered AdaBoost. So I think we have discussed some of the motivation of doing so, because by reviewing the conclusion, the discussion in week 7, we also realize that the analysis here depends on the fact that this edge is a fixed edge. However, this edge has been selected from the capital H, the family, according to D. So to ensure that this selected H from capital H also still keeps this guarantee, which means we didn't encounter a situation where the training data set happens to be an unhappy combination with H. We need this conclusion for everything in the capital H. So our guarantee here will be, well, you can see magnified, not guarantee magnified, but the possibility of encountering bad luck is magnified by sorry, talking one thing, writing another. The capacity of H. Therefore, this motivates us to use small, weak sample H family rather than complicated ones. And by composing the small ones, we can somehow, using the guarantee we can get from the sample model family, generalize that, apply that to more complex model family, which means we can gain the capacity without sacrifice too much on the complexity. So that's the motivation why we want to combine simple models to build strong models rather than build strong models directly. Why we want to compose a lot of simple decision trees rather than build a complex decision tree that can handle any situation. So with this in our hands, we consider some algorithms of building composed advanced machine learning models. We consider like a bagging method and rainforest, stuff like that. So, and we realize that the important thing here is not to how to build a voting system, but the important thing here is how to come up with the weak classifiers or predictors that they are independent with each other. So I use this perp to represent they are independent, but this is just, this is not rigor, okay? they are not in some sense like mathematical sense in perpendicular to each other, just to represent this concept. So to achieve that, we will adopt a method that of resampling our data. It would be as if we have multiple training data copies and we learn a copy of the hypothesis from each resampled copy. And in AdaBoost, well, the resampling is done by how each individual data samples are represented. We resample it just randomly at the first, and then we learn a weak classifier, maybe H1. We evaluate H1. If H1 has some error on the ensembled error rate on the resampled data, so we will give H1 some weight. The weight would be higher. Remember that, consider that. That is the error, and that is the weight. The weight will be higher if the error is small and lower when the error is large. So in particular, in this way. And the next step, we do some very clever strategy. Before we go back to resample the data, we reweight the data points by applying H to the data. And if H has been correct on the particular data sample, we think that is easy. We shrink its chance of appearing in the resampling. If H was wrong on some data sample, we think this is difficult. We would like it to be overrepresented, and we enlarge its weight. Okay, so that is basically what we are here. And in this and the next lecture, we will consider well, another rich family of composing simple models into complex ones. And we will study a new strategy of doing so. So basically, we will consider neural networks. Okay. So, well, welcome, people. I reviewed a little bit slower today because we are still waiting for people to join us. Now we have enough number. Let's go. I address, while you are doing the polling, I address some of the questions here. There is a question that when we do our video representation, do we need to present? You are encouraged to present yourself in front of the camera, but if you do not like so, it is okay. It is up to you. Okay, thank you very much for following along. Now, today let's consider the neural networks. So let us first motivate the neural networks. Okay, by its name, neural networks that has another name called multi-layer perceptions. So both the perceptions, neural networks is clearly connected to their biological counterparts. That is how our brains process information using neurons. Okay, let's consider that motivation anyway. Recall there is one limitation of the linear models we have discussed before. we remember that it is impossible to construct a linear model that can split, that can separate the two classes on a two-dimensional data space, in a two-dimensional data space in such a way. Okay, they are simply nonlinear separable. Okay. Well, the reason for that, we can appreciate, I think, better using code. Well, the link of this notebook has been published here, as you can see. So you can follow me by using the in-class notebook here. But it does not matter. If you cannot follow, you can just if you cannot follow me programming, you can just follow the session. Okay. Here is some visualizer. Remember let's recall our perception model. Okay, it's wrong. The virtual machine is a little bit slow today. Okay, it works. So let's review our perception model first. If you recall that, I will do a perp. Okay, if you recall that, the perp, let us see, we are doing the two-dimensional perp, and without considering the offset constant. So the important thing in a perp is two widths. Okay. See, let us make it that way, maybe. Remember, what is needed to predict on a data sample would be right. So this will be our A value. I ignore the B thing here, but it does not matter if you add that later. And we do something about this A value that corresponds to our review discussion here. Okay, so the simplest decision making we have discussed in the perception model is just to return 1 if A is greater than 0, otherwise -1. Okay, so let's check how the model behaves on the two-dimensional data plane. I instantiate one of the class, and I use my simple visualize step. Oh, what? Yeah. So for some reason, there is a naming convention that we use the word forward for things in neural networks, and the meaning will be clear shortly. Anyway, this is just another word calling that. I will make that explicit by wrapping that rather than implementing that independently. Forward, I would just return whatever returned by my predict. Okay, so basically they are exactly the same, just have two names. Oh, this should be solved. Hmm? No. That should be XY. Sorry about that. This typo thing. Well, you can see. You can read the screen here, like when X is this X refers to here, the Y refers to here. Let me change the name of the visualization to make things clear. So X2, X0, X1. I will name the two axes as X0 and X1. Okay. Let the color to be A. So just to make things look prettier. Now it is clearly. Now when X0 is this and X1 is that, you have the prediction A is 1. Otherwise, you enter the realm where A is -1. And you can change here, for example, if you change the weight of the perception, you change its behavior on the data plan. Okay. Well, we want to generalize this model. We want to generalize that model in the same sense as we want to combine simple decision trees into complex model. We want to identify some points in the perception model to generalize. Okay, so let's start our adventure. For some reason, I would like first to take a look at this point, the decision-making point. That will become convenient a little bit later. But anyway, I will try to convince you that we do not necessarily using such a hard line decision making. We can try to maybe produce a probability of the sample belongs to the positive class, which means I can maybe, instead of generating -1 +1, I can generate like with we going into the realm of the positive class, we get more and more confidence that we will have a positive class, and when we go this direction, we will be less and less confident. Actually, we will be more and more confident that the model belongs to the negative class, which means the model belongs to the positive class. For probability will become 0. To do so, I will encounter another way of making decisions. Decision making 2. What I'm doing, I will return a sigmoid function, which produce nearly to 1 positive value when the input is large, and it will generate nearly to 0 value when the input is very small. Okay, this will be given in such a way. Okay. Can you see this guy? Now, when we go to this direction, it's more and more positive. We go to this direction, it's more and more negative. Okay, we have some, we first generalize one element in the perception, that is the decision making. Decision making can be anything that is not the same as the number. Well, I think I misused the name, the shape. So the pre-transform and the post-transform should have some curly nonlinear relationship, such as this one. Okay. I want to implement this this generalization here, maybe. Okay. Now I can specify the active function. This is a very bad naming convention here, and I will use my active function here. Now you can specify that. Okay, now we're ready. Let's touch some more interesting stuff here. Okay. So you think that when the data space in such a way, and I can only cut a line, which means I can only choose a color. Okay, and for my classification boundary at some particular color, I will never be able to pick up this region from this one. Okay, but how about if instead of using the x0, x1, maybe I treat the previous x0 here. How about if I use, I'm trying to, in the same data space, I'm trying to using the same format of the model, but using another data space. For example, how about if before I apply my weights, I do something about this input. I do not change the amount of information I have. I can just try to handle my input in a different way, as we have learned in our high school mathematics. Let's try to build some complexity and a curly thing here. I give you some trial. You can try to follow me, and you can try to be creative by yourself. Maybe I can take the square of this one. Let's see what we have now. Slightly interesting, right? It seems that we are, although this is still not this one, but seems like we can start try to carve some particular region from the data space rather than have to be happy with the boring straight lines. Okay, so and how about doing this. That looks promising, right? Okay, I got, yeah, I remind the student here. I got a comment from the chat box. Yes, in Python, everything is a first class object that includes functions. So this is totally evil for people come from like Java or C. But in Python, everything is an object. A function is just an object that you can add a pair of parentheses and add something here for it to do something that is called a callable object. Actually, Python can tell you if an object is callable. It has this way of determine that. Okay, whatever. Yeah, later. I stop playing. Anyway, let's discuss the function. Let's discuss the data model. Okay, now we are certainly looking into some promising line, right? It seems that if we can do something about here, we will be good. Why not? Let us continue our generalization of our model in such a direction. Okay. Let us transform our X and instead of using the X, let's use the transformed X. Okay, and the transform X is we can do similar here, but now let me just write that down in a simple way. I will use something for the transform like I will define the transform one here. And as we have discussed, we return, given the X, we return two things. One is X0 square and X0 times X1. Yeah, let's go. We should have the same result. Just we now have write the thing in a more generalizable way. How generalizable? Okay, let's give that as an input argument and when it is null, we give some default. Default transform is do not do transform at all. Or maybe I do some lambda XX, which means input X, output X. This is just a way to write functions that is so simple that it's not worthy worth a definition. Otherwise, okay, and now we give the transform function to be. So we should have the same result again. But now we have things to play with, right? We change decision making. Ah, looks right. Okay, we change the transform. This will go back to the linear, way. Please try to play with that. This is a super interesting thing to work with. Transform 2. Let's do some crazy thing maybe. NumPy. Oh, here is still transform 1. I need to change this to transform 2. See what will happen. Okay. It looks like we are looking into a totally entire new realm of all the possibilities. See how is the classification boundary in this case? Super interesting. I'm letting you to play with it by yourself while you're telling me, are we good? And you can ask me questions. Another question here is about assignment 3. That means if you, this is about the understanding of the time limit. You are right. That is an up limit. There is no down low limit of that. You can do as simple as possible as long as you cover the points. You won't lose point if you do that in a shorter time. Yes, we will do 2 quizzes today, but the second one will be very quickly done so that I can give you the answer of the last 3 questions for people happen to get to be lucky to answer those questions. And of course, the recording of my explanation of the questions has already been available while I was doing the Wednesday class. Okay, seems that a lot of people are very happy with the progress. Let's go. Well, now we are starting building real neural networks. The next natural question is, okay, Jim, you have shown me we have rich possibilities of doing things like this or that in such an extension. And the only question is, given the data, this is also of course, only a sample toy data. When we are given the real practical data, how could I come up with some of such extensions so that the model will realize its capacity to help me fit to the data? It needs to be super clever. Well, in a sense, for a very long time in the business of machine learning, the question might be, yes, you need to be super clever to construct such transformations. And you can see, as you have already seen, that the transformation is all you are concerned with here. Okay, so and you pay people like me to do the business. But then people realized one thing: all you need is some form of transform of the input. Well, then why not let us try to consider this guy itself. The perception is a transform of data itself, right? So the idea is super clever. So, I would use another perception and use that as a result for my input. Let us just implement this idea. Okay. To do that, I need to define that transform here. 3. Okay. Let me define a PP0. I do not need to consider any cleverly designed transform. No transform in PP0. Okay. And in this transform, what I'm doing, PP0 transform X. Yes. Now, how about if I change the weight of PP0 in another way? This is not super obvious, but you can see that there is some interesting pattern to form at the boundary area. Okay. And what is more is this is not only limited to one input. You can do every input for this. So which means we can copy the mechanism here. We're still in the first layer, but do another perception. Also use something transformed here. then starts looking very interesting, right? Okay. And actually, you are not limited to using the same number of neurons. Now I'm starting transform my term from our previous modeling into neural networks. Okay, you not need to use the same number of perceptions or neurons as the original number of inputs. You can form from these two inputs to make more neurons than the inputs. You can do such a way. Right? So let's try. Okay, so what you do here, you will encounter an error. I show you. No error. No error isn't right. Okay, there should be an error. That is because I would need something like that. And then I should have some error. No, that is slightly. I didn't have error, but I still do not let it work. That is because this only takes the two inputs. I need to change this behavior. I need to change the behavior to, I need to take whatever inputs there are available. Okay. For H and W. Zip. So this will take into account that there are extra neurons. Look, it's the third one does have some influence. Okay. Okay, congratulations. Basically, that is how the computational model of neural networks forms. So all the others are technical details. We will discuss some of the important ones for the rest of the time left, this and next lecture. But this is the computational model of neural networks. And there are very beautiful properties of the model. For example, although given the input and directly from the output, you can only have a boundary of a strict boundary. But whenever we have employed another intermediate layer of the same computational model, we suddenly enlarge the computational capacity of the model such a way that it can approximate almost any function from X to Y. It is a rich, strong model. Any questions? Go ahead. I listen some of you. I got a question of the hyper function here. Jocelyn, can you speak up if it's okay for you to just ask me?
Yes, I get a set is unsubscribable error. I don't know what that means, but I don't get the visualizations of the graph. I think it's a syntax error or something.
It's a possibility that the model itself you have given it has some issue. Then it encounter issues here. But in any case, I just copied the text of the function into the chat box here, so everybody can see. This is a very simple thing. In case sometimes people ask me about that, this is none other than I explicitly take any single point that I care about on a two-dimensional plan and let the model to evaluate at the point, and then give you some real like nice eye candy to show the behavior of the model. Say if I make the sampling coarser, you will have seen the magic behind that. So I just sample every 0.25 rather than 0.05. Now the magic disappears and you can see how that works. I just take one data, well, imaginary data sample here, another data sample here, and let the model evaluate here. It does not change the nature of the discussion, just gives us some idea of how the models work, how the model works. Okay. Yeah, I need only to emphasize one thing. And I think by emphasizing this thing, that motivates our discussion about the efficient way of reformulating the computational model. Okay, well, so in any case, let's just consider one thing. There is only one virtually important part in this. I show you the lack of this element. See, let me destroy this guy. Okay, I just use one line of code to make this a trivial thing. It is whatever you give to me, I return to you. Basically, I'm nothing. Based on this, I can just let it to be none as well. It's okay. The same. Let's say the behavior of the model. What? Anyway. Oh, no, sorry. It's anyway. I think I have made some mistake here, but doesn't matter. My point is to let it to be a trivial function. Look, everything has been back to the linear case. if you consider the classification boundary, it's been reversed back to the linear. On the other hand, if this works as previously, I think that is because we haven't employed a B value. That is why we have a positive classification anywhere. But it is clear that we can make boundaries nonlinearly in the second case. So the point is, when we disable this activation here, we encounter in a situation, we will get into the situation that all the nonlinearity disappeared. This okay. You can see that if this is because the previous all positive classification is because the value range now is from 0.5 something to 0.85, but you can easily add another like a B value here to make it a non-trivial classification boundary. So in any case, the important thing is the structure, the complex structure disappeared if we do not use this thing. If this disappeared, all the structure disappeared. So why? Okay, let's think that in this way. Recall our computational model in such a way, we consider the inner product of a vector and another vector. If we write our x vector here, okay. If you remember something about matrix and vector matrix multiplication, when we represent the inner product, we write things down in such a way. Right? So consider this pair of vectors. We write that let me read it. Okay. And this multiplication will take this element with this one, this element with this one, and that will give us A0. And if we consider the computation of this neuron, we would have no, I missed this. Okay. On this side, we still use X0 to combine with this weight and x1 combined with this weight, and this will give a1. And for this one, similarly, we get a2. Okay. This computation is represented as this is a matrix. This is a matrix, although this matrix is only one line. Okay. So, and this will give an A matrix, such. And this A corresponds to this. I'm not saying this A is this, I'm saying A is corresponds to this. A line of values that has 3 values per input. Okay. And the beautiful thing of that is another aspect is that using this formulation, we can handle multiple input data in the same time. If you have a data, input X here, you can write it in this way. If another sample, you can write in this way. Each sample is a row of a table. And then you will have a corresponding row of the output matrix, while keeping the W the same. So now, please try to remove this complexity in your imagination. Okay. Things will be easier. And what is more interesting is this this thing does not only apply to one layer, it applies to every layer. If you have the input value here, I run off the color again. Now let's use the rainbow one. So let's call that H0, 1, 2. Okay. For this layer, let us just use U, because I hate to add too many subscript or superscript onto the same letter W. Okay, that's just U. Then you have U1, U2. Combine them together. You have the final output. Okay, so here we have a situation. I do not know if you have realized. Look, now to have the final output, I just use Y_TOTAL to represent that is a hopeful approximation to Y rather than the Y solve. Okay, anyway, now we want it. And we want to compute that from X. We use X to multiply W. And then we multiply this result with U. And we see this would be the output of our neural network. There's an issue. If you remember a thing of linear algebra or basic algorithmic rules, multiplication as an operation is associative. So which means we can do this together, let it to be V, and this will become this, right? Well, you can represent one layer of neurons as the multiplication of the input to some width, some parameter or weight matrix. This relationship is mutual. You can also represent a multiplication as one layer of neuron computation. So therefore, we have collapsed our neural network. So for how many layers we have, if we multiply them together into one weight matrix, we then can have an equivalent neural network that work in the way that the multi-layer works. Just use one layer. So this is not the desired, desired behavior here. How can we prevent that? Okay, we do some activation function, which is the decision making to here. This is not linear. Let's call that phi here. If you put this here, then you prevent the association here. The computation has to go along the information processing pipeline as defined by the network structure. It has to go this way. You cannot prescribe another equivalent thing that simplify everything. It has to go this way. The information flows from this layer forward until the final layer. And that is a name, forward. Okay, are you still with me? I know, I understand. We need some time to review, warm up ourselves about the matrix multiplication. Yeah, bear with me for a moment longer. Because I want to try to quickly preview some discussion we will do in the rest of time of this and the next lecture. So the nature question, the next the next question that will face ourselves very naturally in our way is, okay, look, previously we are in the route of removing personal expertise or the dependency of how smart an engineer is from the picture. In the first place, we have removed the design of the transform function. We do not use the cosine, sine, whatever complex functions. We use yet another layer of neural networks. We have the neurons, we use the neurons again. So we use this in two purposes. We use them recursively. And then it seems that it comes to the point that the transformation, how transformation is well or is bad, depends on the the specific choices of the parameters of this or of this W matrix, right? You change the matrix, you change the entire landscape. Then how to determine these parameters? Well, we will adopt the sort in such a way. We let data to automatically determine those parameters. How to achieve that? Look, given the input x goes 0, the neural network structure maybe call that the neuron 1. And now you have h, which means the intermediate result here. And you go to another processing step, right? So you go to your prediction. Remember that comes with x, we have another piece of information. This is where the signal from which we will adjust our parameters comes from. Uh-oh. How? Recall this guy. This little guy here. The loss. Okay, how? Let's consider an example. If for the given if for example x0 is 3.75 and x1 is minus 3.6, maybe this way. Look at the output here. If I know that the class here is negative, and which means the confidence of being positive should be 0, right? Then we have now the confidence is 0.27. So we can compute some costs out of this fact that we want it to be 0, but it is now not 0. We want to decrease that. In any event, this just is an example, but this point to the situation that the output on known data points of the model is different from what is desired on those models. And therefore, this difference gives us information on how we should adjust the parameters model so that the output will move into the direction where we want it to move. Okay. To achieve that, we will try to compute that in another direction. We start from the end. How? But please forgive me of using a simpler example, because to compare the confidence of something with the actual outcome of something needs us to employ another piece of knowledge, which is entropy. That means if you remember our study of entropy, that includes a situation where we think the event is in such a probability distribution, however, it is in another probability distribution, and we compare these two situations. This is a little bit more complex than we directly compute the number of 0 and 0.27. Okay, so let's just forgo this complexity for now. We consider, well, we just want to decrease the confidence here, or we just want to decrease the output of the model here. How can we do this? Okay. We first start from the easier end, the more direct connect to the Y and L. So say inappropriate okay. Let us see, our L is just 0.27 and the desired values square error. Then I would like to ask the what if question. What if I change the prediction by I explicitly say positive? Then L would change accordingly by some number, right? So let's just call that L1. What I really concerned is, okay, if I change prediction by delta prediction, how that will get a delta L, how the relationship between the two changes to compare the relationship, I take the ratio between them, which is none other than takes the derivative. Recall yourself some calculation in the calculus class, okay? So what we do, before I hit the wrong, remind yourself in your brain, what should be the number? Okay, something like okay, let's go there. So anyway, we have a number here, and this number is a knowledge. The knowledge is, let's call that G. The ratio between a change in this element in the computation and the corresponding change that would incurred by this change. You would ask why this is important. I want to know that how should I change my model parameters? But you tell me if I change this, I would change this. But that is useless to me. How would I know? How can I change this? Well, that is a good question. Then the next question would be, now, because this is known that if I have changed my prediction such a way, I would change my loss that way. With this knowledge, I would consider this. Okay. Now I know what if change U1 by delta U1. Consider this question. If I change this by a delta U1, the prediction will change correspondingly by H1 delta U1, right? Okay. And this will become, then I would have changed prediction by H1 delta U1. And I already know that if I change my prediction by something, I would change the loss by something, by G prediction, right? I have already known that my prediction will affect my loss in such a way. Then if I know that this will change my prediction such a way, I would just times this. This will be the change of the loss if I have changed the U1 by this. So correspondingly, I will have the ratio between the change of the loss and the change of U1 that will tell me that G U1 will be H1 times G prediction. Okay. let's implement that in a very explicit way. Okay, so let's prediction to be I just make up numbers here. It's 0 to be maybe 1.0, U0 to be 0.1. Okay, these two will give you 0.1, and we need the 0.27, right? So okay, I just come up with numbers. Let's that to be C 0.5 and U1 that to be 3.4. Okay. What? Oh, this is shame. Okay. Okay. So oh, doesn't matter. Okay. Because it's a difference between 0 and 8, so I just use this. Okay. And you know that, take this as knowledge. Okay, we do everything again, but now I'm directly showing the change of U1 here, right? Now, this L1 and this L, the difference will be the incurred change of the squared error due to the change of U1. Okay, so why this becomes 0.7? That is because, remember this guy is 0.54, and this times this 0.5, it becomes 0.27. Or maybe I will remove this to make things a little bit more clear. Let's change this a little bit to make it slightly more clear. Okay. I don't know what it is, but seems to be need to be some value here. Let's see. Oh, sorry. Okay. Now let's see that. I would argue this would be 0.54, which is the gradient of the prediction times the ratio between the change of the prediction and the change of U1. So that would be 0.8 times 0.54. Okay. And the beauty of that is using the same computation, you can compute the what if questions of all the parameters here. Then you would have the parameters here is called U, right? Then you would have G, U. And with this, you can also have the GH. So that means what if I change U, I would change L. What if I change H, I would change L. With this, you would compute GW. What if I change W, I would change L. And the other beautiful thing here is because I know the following argument is needs time to think, which we do not have. So I just give that knowledge to you. You need to reconsider it back if you are interested. So when you compute that, using matrix multiplication in such a way, so the element of H here, I would use A maybe. The element of A here is the multiplication of this and the corresponding column here. And you know that if I change A, if I change this element, I will cause a change of the L in such a way, which called the dL over dA, maybe G, this element. Let's call that the G's. So that is the element in the GA. GA has the same number of elements as A because you need to calculate individual A elements influence on the final loss. Okay, so when you know this knowledge and you want to infer the influence of individual W elements on the L, well, you can carefully collect or attribute the credit of the change here to W. You can consider, okay, how this element of W affected the element in A. It turns out that to get GW, you still have the matrix multiplication of GA and X. And that multiplication corresponding to collecting the contribution of the W element to the element in A. And the other beautiful thing here, I just to mention, we have a, I hope you can, we have to talk about the quiz. Let me go quickly with the quiz. With all this knowledge, we are able to do the quiz. I want to show you some interesting thing, but maybe in the next lecture. Okay, so the take-home point here is we have a backward run of computation in which we attribute the contribution of each element to the final loss. And then we will have the information of to which direction, so to increase an element or to decrease an element. We have this knowledge to help us to train the neural network model. Okay, I quickly go through the quiz such that you have the good basis to do the assignment. And hopefully I can show you some beautiful reference of this quiz. In quiz 9, okay, question 1. We have 4 input data and 16 intermediate level neurons, 1, 2, 3, 4. And for one element in the intermediate layer, You have 1, 2, 3, 4 weights, and that include this. I didn't make that very explicitly. Remember, in the perception model, there is a constant offset, which is B. I mentioned when I'm implementing several times, but I haven't do that in our code. But you keep in mind, there is a parameter here. So for this one, it will have 5 parameters to specify this neuron. You have 16 of it, so totally you have 18. That's 16 by 5 parameters. And for the second layer, you have 16 inputs and 1 bias. So it has 17 parameters. The answer is 97. And question 2. In question 2, it is just to state what we have introduced before, that given enough neuron, a neural network is able to approximate whatever function. So the capacity of the computational model is high. It can approximate any relationship between X and Y. And the non-conflict is just a fancy way of saying that the data is not crazy, that you have 2 answers for the same input. So this is true. It can achieve 0 training error. Without nonlinear activation, as we have discussed before, it will collapse into 1 layer neural network. So it will it does not improve the model capacity because the neural network is equivalent to another one without a hidden layer. So to summarize, 97 is true to achieve 0 training error. Without activation, no improve of the model capacity. Okay. Well, in question, where is question? Is here. By the way, the deadline of question is not in this week. It has been set to the next week. I make this available and discuss this early just to help us to do the assignment. Okay. So question 1 looks overcomplicated, but the essence of that is saying, for a neural network, given a lot of model parameters, what you are concerned is 1 loss. And for each individual model parameter, there will be a corresponding this responsibility quantity that describes how this particular parameter affects the final output. So there are 83 model parameters and 1 loss value. So not 83 loss value, these 2 are wrong. And the gradient vector has 83 corresponding partial derivatives. Partial derivatives is a fancy name of calling the ratio between the change of the parameter and the corresponding change of the loss. So 83, 1, 83. Question 2 refers to an interesting point, which is that we have discussed that the nonlinear activation is very important. Okay, but it does not necessarily like you might imagine that it has to be some curly thing. No, not necessarily. It can be some very in such a way. it still looks very much linear, but just piecewise. As long as it's not globally linear, it will break this association. Okay, so this kind of activation has advantages to disadvantages. Here it discusses one property it has is that while the input is in this region, the change of the input does not incur any change of the output. So basically, look, when this is a computational model, okay, when h is 1, u0 is 0.5, so this is 0.5. And this term, second one, is -1. So the result would be -0.5. And then if there is a little change at -0.5, the output change is 0. And if there is a little change of the quantity that used to compute the -0.5, the change of the output is also 0, which is very easy to consider. If this is 0, then whatever contribute to this will contribute nothing to the loss either. So the answer is 0 and 0. And question 3. So it refers to some understanding of the backpropagation. Oh, well, there are two aspects of that. One is, look, while you continue doing this, you will find the effect of the change will be multiplied along the way from the output to the input. So if you change something in W, it will correspondingly change H and correspondingly change prediction, correspondingly change L. So to achieve, to figure out how this will affect that, you will do the multiplication here, 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 here. Multiple multiplication that created difficulties in the early stages of training neural networks. So this question refers to the knowledge here. Due to the multiplicative nature, the derivatives of parameters used in the early layers is more difficult to compute early, not the late. Late means that is close to the loss, which is slightly easier to compute. I mean, the effect is easier to compute than the earlier part. So then given the gradient, which means given how the individual parameters affect the output, it is non-trivial to determine how much you'd like to change. You know, if you increase that, this will increase, then you know the direction of change. However, just to take an example here. The influence here would be 2x, of course. Doesn't synchronize, doesn't matter. This is 2 of x. And 2x is, of course, depends on where x is. Then if you change according to this information, x a little bit, this information itself changes with x. Therefore, you do not know how much the step size within which you will approximately have this value. So it is difficult to determine the size of the parameter update. To summarize, 83 model parameters corresponding to 1 loss value and 83 corresponding partial derivatives. With this kind of activation and you are in this area, well, the change of this will not change of the output, and the change of whatever lead to this will not change the output, 0 and 0. The early stage parameters associated with the early stage of computation, for those parameters, derivative is more difficult to compute. And given the gradient, it's non-trivial to determine the step size. Okay. Okay. There are, well, in multiple aspects, you guys are in a very advantageous position than people engaged in this area earlier in machine learning. One thing is, if you want to study neural networks, you do not need to manually derive the gradient. When I remember when I was studying that, one particularly hairy math that is a very bug prone is to derive the partial derivatives with respect to matrix. And now you have a very beautiful tools. Look at this fantastic matrixcalculus.org. Okay. Consider if you have a matrix X, and you times that with W, so that you have the prediction, and you compare the prediction with Y and take the so this is the prediction minus Y would be a column vector of desired values. You take that, you take the square error of that. Okay, what you have, you will like X times W minus Y takes the transpose times itself. So let's write this down. X times W minus Y and takes the transpose and times itself. Okay, and you see W is a matrix, Y is a vector, S is a matrix. Okay, and you want to compute things with respect to W, because what you can change is something in W. Okay. Oh, sorry. W is also a vector because now you have only one neuron. Sure. So basically, you are doing things. This is X. This is W. This is Y. Okay. When this is for the final layer of a neuron network. Otherwise, you can in the intermediate layer, when W is also a matrix and Y is also a matrix, it's like that. That's right. Intermediate layer, H maybe. Maybe that's the final layer. It's easier. Y is a vector. Okay, you can see it automatically computes the partial derivatives of W for you. What is more, it can generate Python code. And now I have downloaded a Python code. It just a compute. It does for me. Where is that? Somewhere. Functions.python. So look, the function and the computation of the gradient function and the check of the gradient has already been generated. It's super convenient to do study in neural networks. And what is more, you can nowadays you are easily forgo this step as well. You can use automatic gradient computing tools to automatically do everything for you. I will show you this in the next session. Thank you very much for coming, for being with us. Okay. I hope I can release at least most of the marks for assignment 2. We take much effort on that, but please understand, due to the number of students and the limited teaching assistants, is a kind of a struggle. Thank you for understanding. More questions? Another question is about the quizzes. Quizzes are all released this week. To deter, I get another technical question. To determine the size of the update, it is a common phenomenon in optimization. Let's have a look at here. Say if you're, maybe I just show you here. So let's consider x to be numpy dot. So here is a simple function, right? Okay. And we can, for if this is something we want to decrease, for example, you happen to be here, like x equals minus 2.86 and y is such a value. Okay, so no, doesn't matter. What is this x? Okay, whatever. Let's take this here. Okay, you can see at this point, if we want to go down here, you will get this. What does this mean? This means at this point, if you go to the right with delta x, okay, the corresponding delta y would be this value, minus 2.75 times 2. It's like okay. And this is what does mean by the dy over dx. Now, we want y to decrease. If this is our goal, then you find that, well, if I'm going right 1 unit, my y will going down 5.5 unit. This seems to be a good thing. Then your step maybe let's increase x to be minus 2.75 plus 10. And you think by doing so, you will reach somewhere like minus 55. Plus, where is this 7? Something like minus 78. Basically, you imagine you could go there. On the contrary, if you really go this much, you will not reach here, no way. What you will go is actually here, right? So this is what we mean, that you have probably you do not have a good intuition of how much you should go in each step. I have several questions after that one. Let me go over that a little bit. Okay. Oh, the marks of the quiz. I didn't realize that the marks haven't been released. Try to do that. Marks. Okay, now the marks are posted. Week 9 quiz. The next question is about week 9 quizzes. This one, I briefly go that. 1, 2, 3, 4 input. And for 4 input, one perception requires 4 W. Like what we are doing here. If you expect the input has 4 elements, you need 4 elements here. And remember that we can have the option of, actually we should do a constant bias here. And you can do a constant bias here. Which will, like, for example, you can see now the value shift down. Sorry, I think that this, I should not use this transform. Sorry, I should use this. Look, now you have the classification boundary shown up. Remember, in the class, we have the O1 classification. Now here you have, the very interesting boundary here. So where are we? We have 4 inputs. Oh, it's here. And a B here, so that is a 5 for 1 neuron here. And you have 16 of that. That is corresponding to 80 parameters. And the 18 will be given to the final layer. They're corresponding to 16, not 18, 16 parameters of the final layer and plus 1. So 17. Altogether, that is 97. Okay. And this means if you increase the 16 to 1600, 16,000, so many, you would be able to fit your model to whatever kind of relationship between the input and output. So therefore, a neural network with at most 1 hidden layer, but not limiting the hidden neural number, can achieve 0 training error. Well, this has been very clear, discussed very detailed, in very much detail here. You can look back at, I think, from our into 1 hour in our session. I remember approximately that time I discussed this. Basically, we formulate the computation in neural network as matrix multiplication, and because the matrix multiplication are associative, so if you do not include activation, you basically doing matrix multiplication over and over again. If you do that, you can multiply the later multiplication together into 1 matrix and use this 1 matrix to model the entire network structure, which is basically eliminates the network structure at all. You do not have the structure anymore. Okay. Yes, the questions for assignment 3 is available now. Another question is, do we need to prove? You do not need to prove, you just need to show you have understand of why the correct answer is correct. You can also optionally describe the incorrect answers, but that is up to you. In most cases, the incorrect answers is just the opposite side of the correct answers. You do not need to duplicate. Okay, so yeah, if that's all questions, thank you very much. Oh, another question is, do you need to make a slide? No, you do not need to make a slide. You can just talk against the screen. Depends on you. If you think, if you copy everything out in a PowerPoint slide and talk to the copied questions, that is easier, then go ahead. It is welcomed. Okay, thank you very much. Have a nice weekend. Bye-bye.
Hi, John. Can you hear me?
Oh, yeah. Yeah, I can hear you.
Yeah, I just got a notification from Canvas.
Oh, GitHub. Okay.
Yeah, it says something like, can you stop the recording first so that we can discuss?
Yes.